Okay, so this is reverse engineering. Alex already covered static reversing last week, so this is going to be on dynamic reverse engineering. We'll get into what that is in a minute. So first off, by way of introductions, I'm Aaron Portnoy. I've taught this class, or this section of this class anyway, the last 2 years. The last couple of years I did it with Peter Silberman. This year, Soderov and I were splitting it. Stuff that I work on. Anyone here heard of the Zero Day Initiative? One, two, a couple of you? Okay. So I've been running that for a while. I've been on that team since 2006. I also run Pwn to Own. Anyone heard of that? A couple people? Okay. So I run the Pwn to Own contest, and I've done so since that started. And also, I'm on Tipping Point DV Labs, so I'm the manager of security research over there. So that's actually owned by HP now. We do vuln analysis, research, bug hunting, exploitation, all kinds of stuff like that. Basically, we do reverse engineering every single day. So I'm going to try to get you guys up to speed on just some of the techniques we use and why it's useful and how it can kind of speed up the process, because reverse engineering is something that's really difficult to get into and get good at. I started when I was like 15, and I'm still not very good, so it takes a while. So the stuff that we're going to cover today, we're going to cover WinDebug, because that's my debugger of choice. We're going to cover some basic runtime reversing techniques. That's just stuff like using the debugger to help you with your reversing and be able to complement your static analysis efforts with your dynamic analysis. We're going to cover a little bit about dynamic memory, and at the end of class, I'm actually going to drop a zero-day vuln because I needed some filler. So we're going to go through, like, I'm going to give you guys a crash, and we're going to reverse out what the crash is and show you guys why it's an exploitable vuln. All right. So the first thing you have to ask yourself when you're reversing is, why are you reversing? Like, what is it that you're trying to achieve? Because I mean, this is a really large industry. There's a lot of different things you can reverse. You can reverse a toaster if you wanted to. You can reverse hardware. You can reverse software. Whatever it really is. With regards to security, we're dealing with, at least in this class, because your class is called, pen testing and vuln analysis. We're going to cover vuln analysis. We're going to cover a little bit about vulnerability discovery, and we're kind of going to leave this one alone, but the skills you learn for these two can be applied to cracking and DRM stuff and all that interesting stuff. But the one thing that's all that has in common is every one of these sections here, every one of these disciplines, if you want to call it that, you really don't need to reverse engineer the entire thing you're looking at, the whole application. You're only looking at a limited scope. Like, so you have a goal in mind, you need to figure out how to get to that goal. So you have an end, and you got to figure out how to get there. So this is the kind of stuff you're probably going to be dealing with. This, anyone, you all have IDA, right? Have you played around with the graphing? Like, not the graphing like when you hit spacebar, but the graphing like if you right-click a function name and you hit, xrefs from or xrefs to, it draws a graph using WinGraph. Looks something like this. All this is actually an SSH client. I just loaded up in IDA as an example. This node way up here, that's the main function. That's the entry point of the executable. Every node on this graph is a function, and every edge is a call. So by no means this is the whole application, because there's a lot of nodes and edges that you're not seeing due to dynamic calls, and we'll get into that in a minute. But the point of me showing this is that here's a whole application, or most of an application. When you're reversing for vuln discovery or analysis or crash analysis, any of that kind of stuff, you probably only care about maybe that much, probably less. Really, just you need to figure out how to drill down and to get to that part so you can actually be productive. Otherwise, reversing is a tedious process, and if you don't have things that help motivate you, like if you don't find things that are interesting as you're reversing, you're just going to give up and you'll never get to the interesting stuff. So real quick, I'm going to go over some of the static reversing stuff that Alex talked about, and he was kind of giving you an intro to it. I want to show you why it can fail or why it's not complete. The example he gave you was a bit contrived, right? It was just a receive with a buffer overflow, really simple. Most applications are not like that. Like I said, with static reversing, you're looking at a limited view. In IDA, as you guys have all seen, when you load IDA, what do you give it as input? Anyone? An executable, or a DLL, or some kind of object file, or something. You give it one part of an application, a very small part. So you guys are all CS majors or something like that, right? So have you ever written a linker or a loader or know what those are? I don't see any heads nodding. You have? Okay. So if you've written one or you know what they are, you can understand or appreciate the fact that when you're looking at a single module statically in a disassembler, when that gets loaded into a process, a lot of stuff happens. I mean, you're not just looking at, like, there's stuff that happens in the scope of a process that you just completely miss. For example, stuff like this. If you're looking at IDA and you get a call EAX, that's not a direct edge on that graph that we were looking at earlier. That's a call something dynamic. EAX is a register. That can be anything. It can change. Sometimes you can't reverse backwards from here and figure out where that came from. In this case, you can say IDA commented it for you and says, D word, that address. And all IDA is telling you there is that there is a D word in the .data section of the binary. You have .text for code, .data for data, resource section, import section, stuff like that. It's saying that the value of this, it determines somewhere up here that it's actually this D word. If you look at that D word in IDA, you see a question mark. It just means it's undefined. There's no value there, which you can infer means that when you run this application, something puts an address here that's valid, and it gets put in there, and that call actually resolves to something. So the point I'm trying to make again is here is another call graph, right? You have function, calls function, and so forth. If you have any of those dynamic calls, any of these, there might be some implicit edge that you don't know about, like this. So if you're looking at the graph, you're not going to see any of this. So you get a very limited view. And statically, you're only going to get this top part. You won't even know about any of this. So that's why runtime analysis is so important, because you can figure out all these different relationships and figure out how big the thing is you're actually looking at and what you might want to dig into. So another painful part of statically reversing things is if you're dealing with anything reasonably complex, you're going to hate your life if you're trying to look at it just statically. I mean, applications are massively complex, especially the ones that you're going to want to look at for Bloom's, right? So you want something that's popular like Flash or Shockwave or Windows Media Player or QuickTime or Word or any of those. Those code bases are absolutely gigantic. And reversing anything like that statically is a huge pain. Statically is good for looking at it and going, okay, this looks interesting. Let me mark that for later. Let me look, that kind of searching around, poking around, picking little things that look interesting, but trying to reverse the whole thing sucks. For example, does anyone know what I mean when I say vector parser renderer? You guys write code? C code, C++? What I mean by that is there are a lot of applications that do lexing, parsing, and rendering. A lot of media applications. Anything in Office, PowerPoint, documents, any of that kind of stuff. They do a parsing phase where you give it an input file, and it goes, okay, let me read the header. Yep, it's this version. Okay, now I need to read this chunk, and then it breaks out all these different chunks. That is essentially your parser, but you've got a lexer that will tokenize all that. So here's basically this, like generally, what it looks like with the lexer parser renderer and why this is really a bitch to reverse. Here's step one. You read the input into a buffer, right? So I read in a document file. Okay, now I need to split this document file into chunks that make sense. It's just a big chunk of binary data at this point. I need to know how to delineate all the different elements of it and figure out what makes sense and what's a header, what's metadata, what's real data, what's text. So that's what I'll call, splitting contiguous data into streams or chunks or sections. You're doing with an AVI file, which is a media file. Then you're doing it's a RIF-based file format, so it's got all these different chunks with 4CC values and so forth. So when you do that, you save all that info into what I'm going to keep referring to as application-specific data structures. And all that means is, if I were to write this code, I'm going to write a C structure, and it's going to be called Aaron's structure, and it's going to have a metadata size, and it's going to have a pointer to something else, and whatever, maybe a linked list or a tree, whatever it may be. Those are my application-specific data structures. When you're looking at that in a binary, it's not clear. You don't have any type information. When you have source code like Brandon was showing you guys, and then it gets compiled into a binary, usually they strip all symbols, they strip all type information. So all you see are accesses to registers that don't make any sense. You'll see like EAX plus 4, and then they dereference it. So all you know is that's a pointer. I don't know what it's called. I don't know the variable name. So that's, this kind of information is really hard to reverse. And then, of course, you're going to pass a lot of that data to a lexer. So that's a lexer. Think of it as like a tokenizer. So it just chunks out different parts. Specifically, think like XML. If you're parsing XML, you need your lexer, your tokenizer, to be able to find all the brackets, find the end bracket, find the start bracket. Okay, that's an element. Go for this element. There's bugs and all of that. Then you got to store all those tokens into other, unrelated app-specific data structures. And then you got to parse all that data. And then you got to figure out how to render it to the screen, and how, rendering's got all these different problems. You have a screen width, and you have, word wrapping, and you only want to write this much, and you want to write that much, and you have to worry about character kerning and all sorts of glyph data and all sorts of crazy stuff there. So the point in showing all this is that there are bugs all over this stuff. And trying to figure out, okay, you have your input file, you know what that is, that's your data. Trying to get from here to here and figure out where your data is again and how it's influencing this is a huge pain. Especially because your data may be a certain value here. Say your data has, say your input file, your PowerPoint presentation has the byte 12 in it. when it goes to render it to the screen, maybe that was a width, but they're going to multiply it by the number of rows, and they're going to do all this crazy stuff. The value is not going to be the same. You can't just, start reversing here and hope to understand the data you're looking at, because you're going to be looking at all these different data structures. And the most important thing about all this is, how would you write this code? How would you write it? You write it. How would I write it? Everyone's going to write this differently. Every application you're going to look at is going to be completely different, which means all that knowledge, it's not really portable. Like, you do it once, you reverse all that, you're like, okay, cool. I understand QuickTime really well. Let me go look at Flash. Completely different. You got to start over. So basically, this stuff is painful. Good luck reversing any of this statically. Yeah.
Wait, so what transfers over from, like, let's say you have a deep experience with QuickTime, and then you want to reverse something else? I mean, so the application-specific data structures are going to be very difficult to find again.
Yep.
So basically, what is it that you learn from QuickTime then?
So it's not so much the reversing knowledge that you gained about how that application works. It's the techniques you develop to analyze it, which is what we're going to cover. Using your debugger in a way that helps aid you on any project you're working on. How to track data through an application is generic, right? If you know how to be able to, we'll get to it later when we go into WinDbg, but basically if you know how to track data from input to usage in another data structure, if you have those techniques, then all that stuff, that's the portable part. It's the techniques, not so much the specific reversing that you did on one application. And like I kind of alluded to earlier, a lot of stuff happens in the scope of a process that you don't see when you're looking statically. For example, who's here has written an exploit before? Okay, here you go. So you've probably looked at, like, if you're working on Windows, like SEH-based overwrites, right, where you're overwriting an exception handler. Well, exception handlers are all module-based. Like, a certain module will register an exception handler. It gets added to a global list of exception handlers, and when an exception occurs in a process, it walks this list and figures out who can handle it. Now, if you're looking at one module, you only see the scope of that module. You have no idea. Is this the first exception handler? Is it the last one? Where is it in the scope? I have no idea. You can't figure that out statically. Linkers and relocations and module dependencies, that has to do with what I mentioned earlier about linkers and loaders. For example, if you have a specific module and it requires NTDLL, what does NTDLL require? What does, say you're looking at any given module, and you need to know exactly how that looks in the application. Well, the most basic of basic things about that module is not going to be the same in the process, and that is the addresses. So when you look at the addresses in IDA, the addresses that IDA chooses to show you in the disassembly are the ones that they're indicated by a header inside that DLL called the preferred base address. It's called preferred for a reason. It's called preferred because when you load it into a process, the loader goes, this is where it would like to be loaded in memory. However, if there's a conflict, I'm going to relocate it and put it somewhere else. So when you're looking in the debugger and you're looking in your disassembler at the same module, the addresses might be completely different. So that's some other stuff that you're not going to see statically. You just don't know because you don't know what the process memory space looks like. You have no idea where it's going to start putting stuff. Dynamic memory, we're going to get a little bit more into dynamic memory later, but the stuff that Alex was showing you with the stack buffer overflow, that's static memory. That's like a car, buff, whatever, right? So that's on the stack. It's not changing. It's an array. Dynamic memory is anytime you're seeing malloc calls, stuff like that, where it's dealing with heap. We'll get into why that's tricky to deal with later. But statically, you have no idea. You can't look at a mem copy and go, oh, that buffer is of size X. You don't know because it's dynamically resolved, meaning it needs to be calculated at runtime. Stuff like global variable values, which is the thing I showed earlier where it was making a dynamic call and you didn't have that value of where that call was going, that's a global variable. That's something you don't get statically. And this is a kind of tricky one, but what I call out-of-band data. So say your module is like, you have all this code flow it can go through, and you're reversing it and you're like, wow, I'd really like to get over here, but I'm not sure if I can. Well, it could be because there's a comparison for some data that they pulled out of the registry. Maybe there's some data at runtime that they query a database and figure out if you have privileges to get over there. Maybe it's a state machine, and those are really painful to reverse, where you have a loop that just goes and there's a state counter that changes and it goes different ways depending on how all that works. Out-of-band data is just data that's not part of the module you're looking at that can influence how that module executes. So the point of all this anyway is to show you why static analysis is useful for some stuff, like a contrived example when you're looking at a straight-up Stack Overflow from a receive. Yeah, you can reverse that pretty easy. If you're going to look at anything in the real world, you're going to need a debugger because statically it's just not going to cut it. So, any questions so far? No? All right, when we get to the demo portion of all this stuff later, if you guys have no questions, I'm going to have Dan assign it for homework.
You said, like, when a guy is loaded into the EAX register, the pointer gets dereferenced. Does that mean that it just doesn't have the name of the variable that it was stored in along with it?
Are you talking about where that call EAX happened?
Or what does dereference mean?
Dereference means if you have okay, so any register at any point when you're debugging, this is really important. Anytime you're looking at a register, it is one of two things. It is either a value or a pointer. If it's a pointer, it can be dereferenced. By pointer, I mean it's an address.
Okay, I see.
So when I say dereference, I just mean you're dereferencing that address, like think in C, right? You're saying what's at that address in memory. Yeah, make sense? All right, so dynamic reversing. Just going to define this as dynamic reversing is focused on performing all your analysis during runtime. If you want to think of this theoretically, dynamic reversing introduces a new state to your analysis, or rather a new dimension to your analysis, which is state, meaning if you're looking at a debugger, you have context. Right? If you break an application, or by break I mean stop an application from running at any point during its history of running, you are currently at a specific state in that application. The registers all tell you something about how it was executing. You can look at the call stack, which is ESP. That'll show you where you came from. You have a path of how you got there. And that all is very useful information. We'll get into that in a minute. Basically, dynamic reversing is intended to supplement all the stuff that you're going to do statically, like the dynamic calls I was talking about, like the out-of-band data. Like, can I get to this interesting thing? Like, if you're reversing statically and you find what looks like a stack buffer overflow, it'd be great to know if you can get there. It'd be great to know if that data was even yours that's being copied into that buffer. So the most important thing about dynamic reversing, at least when I'm doing it, is that it allows you to validate or disprove your suspicions or your assumptions. So if you're sitting there looking at something statically in IDA, and you're like, well, that looks like it's parsing user data, but I have no idea. I think that I can get over here. I think that this is, a vulnerability. I think that this looks interesting, and I think I should be able to get there. Well, you're able to validate all this with your debugger and be like, okay, here's why I can or can't get there, and here's how I might be able to. So just to get this out of the way, dynamic reversing or analysis doesn't actually require a debugger. There are many different things that fall under dynamic analysis. Basically, anytime you're analyzing or viewing or monitoring an application and while it's running can be considered dynamic analysis. You don't actually have to be invasively attached to the process to look at it. So I'm thinking stuff like, you guys are on Windows, netstat command, right? Or TCP view from sysinternals. Just those are applications that show you what's listening on the ports on your computer, right? That's useful. That tells you something about that application. Things like process monitor, which tells you every time it hits the registry what keys it was accessing. All that kind of stuff is useful. We're not going to really go into that. I'm going to stick with just debugger stuff because I think it's more involved. How many of you guys have used a debugger before? Great. Which ones? You've used WinDebug?
Who counts?
What? What kind?
Who counts?
Well, the ones I've used, just to throw it out there.
Ollie?
Ollie? Okay, Ollie debug. You used Immunity debugger before? Yeah. All right, so Ollie debug, Immunity debug. Immunity debug's based on Ollie debug. Ollie debug, WinDebug. Those are Windows debuggers. You've got there's one called the Rasta Ring Zero debugger. You've got KD for kernel. You've got GDB on Linux, and got ADB on some other random operating system you don't care about. But they all have stuff in common. They basically allow you. We'll say instrument, even though it's not the technical term, but they allow you to interact with the process and monitor what it's doing at any given point. We're focusing on WinDebug, and I'll tell you why in a little bit. So when you're going to be in WinDebug and you're reversing dynamically, your main goal is to be able to drill down and figure out what it is you care about. If you're looking at a process has a lot of stuff going on. Probably got over 15 to 20 to 30 to 100, if it's a really complicated application, modules that are all loaded in that process at any given point. You need to know what you care about and what you don't care about, again, so you don't waste your time, so you're efficiently reversing. So module dependencies can help you here. I think Alex may have showed when he was looking at that binary he had the other day in IDA, he looked at the import section, he saw that it called received, and then he cross-referenced receive and saw that, oh, it does deal with network data. So you can tell a lot by what modules a DLL imports. Here's a way to do it statically, just to throw this out here, because it's a really cool tool. Dependency Walker, just kind of, we can look at user32.dll, which is system DLL, and you can see that it requires NTDLL and GDI and kernel 32 and stuff like that. That's useful just because one of the first things you should be doing when you get a module down is like, all right, well, from a bird's eye view, what does this thing deal with? Does it deal with the registry? Does it deal with the network? Does it deal with file I/O? What kind of stuff does it do? And once you found that, for example, here's a module I loaded in IDA. I went to the .idata section, which is imports. I see that it has a registry open key XA, which is a function that just opens up the registry key in Windows. And you can cross-reference that and see it's called 47 times. That's useful. Now I know it deals with the registry. Just random things that you're going to want to be looking at when you're reversing stuff. But the most useful thing that you can get out of reversing or looking at these modules is, how do I know if I ever actually reach any of this stuff? You can look at it all day statically, but again, you're not going to know if it's interesting or if it's worth your time unless you know you can reach it. And here's where your debugger comes in. All right, so I heard some of you said you've used WinDebug before, so this might be painful for you, but I got to give you guys the walkthrough on this because I'm going to be using it heavily, just to show you guys that bug later. So when you first fire up WinDebug, the first thing you're going to want to do is completely useless unless you're actually attached to a process. In WinDebug, there's two ways to attach to a process, essentially. You have the ability to attach or load, and there's a difference. When you attach to a process, it's less invasive. If you load a process, which means the process is not currently running and you're going to load it and run it with a debugger from the start, then it loads a slightly different memory manager, like dynamic memory manager, which can affect exploitation later. It's a stupid little detail, but it's bit me before where you write an exploit and you've been loading the process every time and then you try it out on a normal process without a debugger and it doesn't work and you can't figure out why. That's why. So anyway, when you load up WinDebug, you go to File, Attach, or F6, and it'll pop up this window. This window has all your process IDs here and all the process names here. And when you attach to one, this is what you see. Right, so it gives you versioning information about WinDebug, and then it dumps all the modules that are currently loaded. You've got the start addresses of all of them, the end addresses, and the path to them. And then you've got stuff down here, which I'll go ahead and zoom in. So everyone can see that was what was at the bottom of your debugger down here. So this is important. This is basically what you're going to see every time you're debugging. In red here, I'd like to show you, but it looks like it's a little misaligned. But anyway, this says EAX and this says EIP. But these are all your registers, your 32-bit registers that Alex was talking about. So here are your registers. Here is your current instruction you're executing. That's your flags. Which flags determine when a jump happens when you hit a JZ. It determines the 0 flag in the CPU is stored in one of these bits here. So that's useful when you're looking at a JZ. Whether the JZ, a jump happens or doesn't happen, is because of the flag value. And then you've got your actual disassembly here. So this is your current instruction. You'll note that this address right here is the same as your EIP, your current executing instruction, right? And then here's the mnemonic for what's going on. So when you first attach to a process, what you see is break instruction code 8003. So this is actually a Windows error code or Windows symbol, basically. It's first chance. That's just telling you that you requested to attach to this process. You are now attached. What do you want to do? So let's give you some basic commands. At this point, you can issue commands. In fact, let me just show you. Anytime that you are dealing with WinDebug and this bar right here, this input bar, is white, that's when you can execute commands. When you let the process go and it's not stopped, this will say busy right here, and that'll be grayed out. You can't actually give it any commands. You have to break into the process. In other words, it's running. You can't, there'd be race conditions if you were trying to interact with it while it was running. You have to stop it. So, most basic of basic commands is the go command. Just G. G, enter. G will let the process go. And if you want to stop it again, you have to hit Control break. So those of you on a Mac, I have no idea what that key combo is, but it exists. You don't have to do it via the keyboard if you don't want to. You can go to debug break from the menu. So that's the most basic one. Then you've got the R command, which just shows you the current register state. So R command is basically exactly what we were just showing on the last slide. It just shows you your register state, your current executing instruction. You could actually set registers values manually that way too. If you do R space EAX equals 1, it will actually change the value of that register. And then the most useful one out of every instruction in all of WinDebug is .hh. .hh brings up the help. If you hit .hh or if you hit F1, it'll bring up the help. If you do .hh and you give it a command, it will automatically search the help and pop up that particular command's help page, which is super useful. Some other basic commands, if you want to actually make the process go, or like go forward, one single step or trace, you've got two options. You have T and P. The difference being T is for trace, which steps one instruction and steps into a function. In other words, if you hit T and you're on an add instruction, it goes to the next one. If you hit T and you're on a call instruction, instead of skipping the call, it goes into the target of that call, its first instruction. Okay, P does not do that. P steps over it. Some random useful stuff like TC. Like there's variations on all these, which is why you want to read the help. There's a lot of variations. But like if you execute TC instead of T, it'll actually trace to the next call, which is useful. And then you've got this command, which we're going to be using later, PT, which tells it to single step all the way till the return of that function. We'll get into why that's useful in a minute. These slides are going to be online, I hope. So you're going to want all this. But if you go to windowbug.org, they have some random person made it. It's not like Microsoft sponsored or whatever, but it has all sorts of commands in Windowbug help because you're going to need all this for the homework, so I assume, probably the midterm. So anyway, another really huge advantage of Windowbug is its symbol support. You guys know what symbols are? Yeah, all right. So symbols are awesome. Not every application has them. In fact, quite a lot don't, but Microsoft applications tend to. In fact, Microsoft, Apple, Chrome, Citrix, all those guys have symbol servers that are publicly available that serve you symbols straight to your debugger. And the way that you say that you want to receive those is you go to File, Symbols File Path, and you put in a string here, which has to be of that format. Don't worry about what it really means other than you need SRV, asterisk, and then your local path, asterisk, and then the remote path to the symbol server. Windowbug.org lists that URL if you ever need it, or you can just Google Windows or Microsoft Symbol Server. And this kind of stuff is really useful because here is a call stack. Right now, the process is stopped at memcopy. Like somebody just called memcopy. And here I execute the K command. We'll go into that in a minute, but it just shows you the call stack. Everyone who's called. In other words, this guy called this guy, called this guy, all the way up to memcopy. Okay? Now look at the symbol names you have here. As a general thing to notice, anytime you have symbol names that have really large offsets like that, like 92D, 9B3, 220E, something strange is going on. And about the format here, the way how this is trying to show us this is we've got NTDLL here, and you have an exclamation point, and then the symbol name, right? So NTDLL is the module, memcopy is the function inside that module. So what's happening here when it does, UX theme, the get theme bool plus 220E. The reason it's doing 220E is because there's probably a crap load of symbols in that module. It just doesn't know about them. So what it does is it takes the only one or two or three, like the closest one it can find, and figures out how far you are away from that, even though there might be a bunch in the middle, because it doesn't have symbol information yet. Okay, that makes sense? Yes? No? Okay. So then when we reload symbols, in other words, we do this stuff, and I say, okay, get us symbols so that this will make a little more sense. And then we do the exact same command. You'll see instead of all these really large offsets, now you have stuff that actually makes sense. Define window proc worker, define window proc, like all of that changed. This is the same information here. Memcopy is the same. All of these symbols have changed to ones that actually make a hell of a lot more sense, which is super useful. And then there's a bunch of Windowbug commands that actually allow you to examine symbols or apply symbols to memory, do all sorts of interesting stuff. Examine symbols is useful. It's the X command. The X command, you can give it, in this case, I'm giving it a module, and then the bang symbol, and then you can give it a wildcard and say, find me any symbol that matches this wildcard, and it'll dump those. You can list near a symbol, so instead of actually searching for a symbol, if you have an address in mind and you want to know what kind of data structure it is there, and maybe it's something interesting, you can do ln. So in this case, I'm already at memcopy, and I do ln at EIP, and it tells me, oh, you're at memcopy. Good to know. And then this one is really useful. We're not going to quite get into what you can do with it, but DT is display type. What that allows you to do is basically, if you have an address, say you have the address, you guys know what the PEB is, the process environmental block? No? Okay, the PEB is, it's part of every process on Windows, and it has all sorts of information about how that process works. In other words, it's got all the information about how the modules are located, all the loader puts all the information of addresses in there, it's got pointers to all sorts of interesting stuff. Every process on Windows has it, and there's a lot of really useful information in there. And it's a really big structure, but it's documented, it's on MSDN. And Windowbug has access to that. So if you ever want to know what the value is of a particular field inside the PEB, you can do DT PEB and give it the address of the PEB. In this case, I'm dumping RTL critical section. And all that's showing you is, okay, it's a structure. It has, 1, 2, 3, 4, 5, 6 elements. There's their sizes, there's their names, and there's their types. That's really useful. That tells you the difference between pointers and integers. That's useful. Now, what's really cool is if you actually apply that to an address, it will parse out all the data at that address and fill this in with the values as well in the debugger. And what's really cool is if any of these are, for example, this is a pointer to critical section debug. DT can actually can be invoked recursively. And you can tell it, apply this symbol to this address, and for any other symbols you find in there, apply the proper symbols for all of those. And if you ever execute that on the PEB and you say do it recursively, it'll just print for like 3 minutes.
So RT alphabetical section is like a structure?
Mm-hmm.
Okay. And then like DT is like showing you the contents of the structure?
Yeah, you can use DT a couple different ways. So if you just give it like I did here, I just say DT structure, it'll just give you the structure there, which is the same thing you can get from MSDN. However, if you say DT structure and then you give it an address, it will actually apply that and go, okay, the first element is 4 bytes and is a pointer, and it will print it out like this, but it will actually give you the value as well, which is useful. And then, like I said, you can apply it recursively, so anything that is not a static pointer or value and it actually points to another symbol like this, it will also dump that and it will indent it out. So it'll be like, here's a PEB and that points to this object, it points to this, and it's pretty useful. Okay, a little bit more about the address space. So I just got to get through all this stuff because I'm going to be using it and I don't want you guys to be lost. LM. So LM command shows you the listed modules in your current process space. If you just execute LM, you get this, or something like this. It just tells you, here's the start address, the end address. These are the addresses that were determined by the loader, right? So remember how I said if you're looking in WinDbg and you've got your address in WinDbg of the module you're looking at, it may not match up to these things, so you have to double check all that. And it gives you the name and all that. You can also do, you can search with LM, M, and then a wildcard like that. And then you can get all sorts of really useful information by doing bang LMI. So any command in WinDbg that starts with an exclamation point is an extension. That doesn't matter too much, but just for your knowledge, I do bang LMI, it's invoking the LMI extension. And what's useful about doing that is it gives you the base address right here. So that's the base address, which is what's going to correspond, which like if you're looking at IDA and you have a module in front of you and the addresses aren't matching up in WinDbg, you can do bang LMI in the debugger, figure out what the base address is, and then you can rebase your image in IDA so that it reflects the image in your debugger, so the addresses are exactly the same. Make sense? When you're reversing, you only care about specific modules in the process space. So if you look here, you'll see all of these. These don't have any paths associated with them, right? It's just the name of the module. These have paths associated with them. However, those are System32. These are all also System32. If they don't have a path involved with them, or like on that line, that means that it's from the default path, which is System32. The only one that doesn't is this one here, C drive, program files, whatever. That's what you care about. You don't want to reverse how NTDLL works, unless you're crazy and you're doing something like Val6 heap research or whatever, where you have to look at that kind of stuff. But in general, if you're reversing an application, you only care about that application's code. You don't want to, or as I say here, you want to avoid STDs, or standard libs is what I'm referring to there, where you only want to reverse the application-specific code. You don't want to reverse the standard libraries on the system. Some other useful stuff. You have all these exceptions, like things that WinDbg can handle for you. Like if an exception happens in the process, what do you want to happen? If a new child is spawned from that particular process, what do you want to happen? If an illegal instruction happens, if a single-step exception, if any of this stuff. The most useful one that I use all the time is if a new module is loaded. In other words, if you're looking at a process, say there's a specific module you care about that you're reversing, right? You're looking at it statically in IDA. You look in your debugger, and it's not even in your debugger right now. You're like, okay, why? Well, something didn't happen yet, and it hasn't needed that code yet, so it hasn't loaded it in the debugger. But I'd like to know when that does happen. Well, you can set the exception for LD, which is library load. I don't know what the LD stands for, but probably load. So set exception enable library, and then you give it the module name. So I can say, like, when this module is loaded, let me know. And then you can just let the process go. Then you use the application, see what happens. As soon as that module is loaded by the process, when it calls load library on it, it'll stop the process for you. Which is useful because if you're going to set breakpoints in that, you can't easily set a breakpoint on a module that's not loaded. You can using deferred breakpoints, but we'll get into that later. Some general usage stuff. When you're referring to anything in WinDbg as a register, you should prefix it with an @ symbol. If you don't, Windowbug's going to try to look that up as an actual symbol. In other words, if I write an application and I use function names like EAX and EBX and ECX just to screw with people, and they're trying to debug it, it'll mess up. You know what I mean? Like when you're in Windowbug and I exported symbol information, you're your debugger and you're like, oh, dump me at EAX. It's going to dump them a function. And they're going to be like, why is that happening? So if you prefix in your debugger with an @ symbol, it tells Windowbug, I'm talking about a register. I'm not talking about any symbols. Don't do symbol lookup. You can reference addresses all sorts of different ways. You can give it an address like a base 16 number, like 0x that number. You can do it by module name. You can do it by symbol and module name, which is what I was showing earlier, where you have a module name and an exclamation point and a symbol. You can do it by offsets. In other words, module, bang, symbol, plus some offset. Just general use of stuff. If you're setting breakpoints or you're dumping functions or whatever, you can kind of reference them this way. And then, of course, you can view memory. You can view it with the D command, and there's all these different variations of the D command. We'll get into these in a minute. Well, a little bit later. They're not that important. Basically, you just need to know that if you need to dump memory somewhere, here's how you can do it. You can do it via the debugger menu as well. You can go like view memory and look at it that way. But in this example here, DC at ESP. ESP is the stack pointer. So this is showing us what is currently on the stack. That, in that order, right? That's useful, and I'll show you why that's useful a little bit later. And call stacks, which I kind of briefly showed a little bit ago, where the K command will give you a call stack. If you do the KV command, it'll actually print 4 D words or 4 32-bit values in addition to the call stack, which is useful if you're looking at like a receive call and you want to know what the socket was, or you want to know what the destination buffer that was pushed to receive is. I'll show you how you can leverage that in a minute. With breakpoints,
Wait,
KV gives you this. All right, so here we are at breakpoint. Oh, you can't fucking see. There we go. All right, so I just fired up Windowbug on PuTTY. I set a breakpoint on memcopy. I let the process go, right? Now, if I execute KV, oh man, this is 64-bit. Sorry. So, yeah, this is 64-bit addresses, so they're not 32-bit. So sorry that it's so long. But basically, what it's showing you is your stack address. So this is current ESP values. Your return addresses. These are actually what creates the call stack, like who called who. And then you have this. This whole section right here is what the V in KV gives you. And those are the values, or the if I want to call receive, I do push socket, push, or push buffer, push size. It's arguments, yeah, exactly that. So a lot of times they don't know how many arguments that they should be showing you, but they show you, by default, in this case 4, but you can change that. If you look at .hhk in Windowbug, crazy amount of options you can do there.
And what's that? What's child SP?
Child SP is a stack pointer.
Okay.
I'll show you exactly what that is in a minute. But first, let's go into breakpoints. So all this stuff I'm going to use in a minute. I just need to get you guys up to speed real quick. So breakpoints. As you guys probably already know, you said you've used debuggers before. You've got software breakpoints and hardware breakpoints, right? Software breakpoints. Anyone know what a software breakpoint actually does to the process? Not using it. No one? Okay. So
put like a piece of code in the actual function itself.
Yep. That's exactly what it does. A software breakpoint, actually, when I say breakpoint at memcopy in Windowbug, if you just do BP memcopy, it actually injects a byte into the program. It injects a CC, like the opcode value of that instruction is CC, which is an int3. And then what that does is an int3 is actually an interrupt, which gets raised up to your debugger when you hit that instruction. So when I say breakpoint on memcopy and then I let the process go and memcopy gets hit, it's only because the process was executing and it hit the int3, which caused an interrupt to be called, which called Windowbug to go, oh crap, that's my breakpoint because I know I set that. Let me handle it, right? So you can actually have int3s in code legitimately. In fact, I've seen it in Safari, reversing Safari, I think, and it's in QuickTime. It's in Firefox. Coders themselves will actually put int3s into their own code when they know they've messed up, which is kind of funny. Like, if they know that they might be corrupting memory or they had some kind of a problem, they'll essentially, instead of doing an assert and bailing, they'll put an int3. which, if you don't have a debugger attached, will crash the process. So you'll see them all over the place. Anyway, so that's software breakpoints. Software breakpoints actually inject a CC byte into the process. Hardware breakpoints actually, they don't. Hardware breakpoints are just that. They're hardware based. You have a limit of 4 of those on current CPUs. You can set them in 3 different modes, either read, write, or execute. And again, you only have 4 of them, so they are probably the most powerful type of breakpoint you can use, but you have to use them sparingly. So the syntax in WinDbg is BA, which means break on access, and you do a space, and you either do read, write, or execute. And then you give it the bit width, which can be 1, 2, or 4, which just means, did they access 4 bytes, 1 byte, 2 bytes? You know, which one do you care about? And here's just some examples of setting breakpoints. I'll show you why these, or how to use these in a minute. And then you've got conditional breakpoints. So you can say, just like you did with the other breakpoints shown prior, you can do breakpoint address, and then you can put an arbitrary expression here. And they take MASM syntax or NASM syntax, if you guys know assembly or have coded in assembly before. And here's just a really, really simple example. Breakpoint NTDLL plus hex 200, and then you basically quote, and all the syntax for this is available in the help, but I'm doing like, if register EAX is less than hex 20, don't do anything. In other words, that'll raise it to the bugger and stop the process. Otherwise, let the process go. And you can imagine when that's useful, right? There's plenty of reasons, but I guess we'll show you when I get into WinDbg why that can be really useful. And then if you've set a bunch of breakpoints, here's how you clear them, here's how you disable them, here's how you enable them, and list them. So you've got the BC command, you do BC space 0, 1, 2, 3, or you can comma separate them, and that'll clear a breakpoint. In other words, completely remove it. BD will disable them, BE will enable them, and BL will list them. Really basic. Yep.
Are there any enormous discrepancies between WinDbg and GDB in what you've covered so far? For example, setting breakpoints or?
Yes. I mean, the syntax is all different, first of all.
Yeah.
And the symbol support in GDB is absolutely terrible compared to WinDbg. Yeah, there's like the GDB obviously doesn't work for Windows, right? So you're missing a lot of the application specific, like the Windows specific stuff that WinDbg can support. WinDbg was written by Microsoft, so it has amazing symbol support for all the different things that happen in a process, like the PEB, or like all the module information, or how they're all loaded, or most importantly, the heap. I'm going to show you a command called bang, or an extension called bang heap in WinDbg, which is available by default, and it's something that GDB will probably never have, just because, well, we'll get into why later, but I guess you'll see. It'll become clear why WinDbg is a lot different from GDB. So, how do we use breakpoints? So we understand that they're very basic and you have the syntax for them, but what is an actual use case for a breakpoint? In this case, we're going to breakpoint on WSA receive. So you can glean runtime information from the debugger when you've got a breakpoint set on stuff that you care about. Intelligent breakpoint. So if you go to MSDN, you can see the WSA receive function takes a socket, it takes LP buffers, it takes a dword, which is the count, and all these different arguments, right? So here's what the stack looks like. I don't know how much you guys have played around with this. I know Alex mentioned it the other day. This is this is the stack at the point of which an application has pushed arguments to receive and is about to call it. Okay? So at the top of the stack, you've got the save return address. That happens when the call instruction is executed. It's implicit. You don't see it happen, but it saves the return address on the stack. That's how when you do the K command to show the call stack, it shows you the return address there. And then you've got ESP plus 4 plus 8 plus hex C plus hex 10, 14, 18, and so forth. And those are your arguments in reverse order. Remember, if we go back to receive, you've got S, LP buffers, DW buffer count, S, LP buffers, DW buffer count. LP buffers is actually a pointer to this structure, right? So this is what the stack looks like when it just called WSA receive. And this is useful because if you're breakpointing on WSA receive, now you can set a breakpoint, and remember how you can give it commands with the expression? You can say dereference ESP plus 4 and dump that to the screen, or whatever it is you want to know about. Or tell me if WSA receive was called with a length more than 100, stuff like that. Here's the point at which you are about to return from the call of WSA receive, meaning you're at the end of the function. It's got your local variables, your save EVP, EIP, and your arguments. Don't worry too much about this. I'm just trying to explain why at any point during the execution of any of these functions, you can grab data out of it and figure out and act on it. So we'll just skip that. But it's basically this, right? here's output from my debugger. So I set a clever breakpoint, I'll call it, on receive. And all that does is every time receive is called, it says receive was called with the size of whatever. And there's your size. Here's your data that was actually received. So instead of having to sit there in the debugger and manually go, all right, well, what did it receive? Okay, let me dump at this address. You can just have it automatically do it for you. Automatically dump the call stack. Automatically set a memory breakpoint on the buffer that was at 188.38, right? And then as soon as it's actually hit, breakpoint 1 is hit, you unassemble backwards 2 instructions and you see that they were dereferencing from EAX. Or rather, it was coming from EBP plus 8. You dump it EBP plus 8, you see there's your address. So let me.
Wait, it doesn't automatically do that. You can set it to automatically give you the cost.
Oh yeah, it totally doesn't do that automatically. But you can write. My point is, if you understand and you can look at the documentation for any function, or you reverse unknown functions, you can set thousands of breakpoints if you want to in the code in the debugger.
Yeah.
So while you're reversing it or throwing, say you're looking at a media player and you play an AVI file, you can just watch your debugger and have it tell you, hey, they were looking for this value in this buffer. Oh, was that value from my file? Like, you can just kind of watch stuff, which is really useful.
Okay, so is that like a trace point or is that a breakpoint?
That's a breakpoint.
So when you watch it, does it like break and stop execution?
It can, or you can tell it to continue, or you can tell it to do arbitrary commands of any kind. Hell, you can even tell it to invoke Python and search entire memory for your name. Like, whatever you want it to do, you can make it do.
Okay.
So, yeah.
Can you export your breakpoint stuff to a file so like other people could maybe like import it, or do we have to do it by hand?
Yeah, I've got a bunch of breakpoints if you want them. Actually, someone on my team was going to post a blog entry on the DV Labs page with what we call pre-print breakpoints, which does exactly that. So not only can you do it on known functions that you're looking at MSDN or you're looking at a man page for, you can actually do it on what I'm going to call implicit functionality, right? So you've got some instruction sequences in, I don't know how much you guys have stared at x86, but there are certain implied instruction sequences that do operations that the developer may have written as a function, like call memcopy, but instead that translates to like one instruction in assembly. For example, this kind of stuff. Anyone ever see rep move SD? Yeah, I know you have. Rep move SD, you'll see it in your disassembly. The developer of that code may have actually written call memcopy. However, the compiler is like, well, I can do this with one instruction. Why do I need to make a call? There's overhead associated with a call. I need to push arguments to a call. The call needs to clean up the stack and return. Why not just make it one instruction? So I just want to kind of show you guys. Actually, let me cover this real quick because this might be confusing. Alex kind of covered registers with you guys, right? You know that they're all 32 bits. You know there's 8 general purpose. You have the stack pointer, the frame pointer. What you might not know is compilers on Windows reserve or use a lot of these for specific reasons. How do I explain this? In the Intel documentation, they'll talk about a lot of functionality, like let's see how to explain. So you've got EAX. If you're looking at Windows and you look at EAX value, after a call, EAX is almost always going to be the return value of the call. In other words, if you call memcopy and it copied 20 bytes, EAX will be 20 after the call. That's implicit. You don't see that happen. Okay? You'll see it if you dig into memcopy, but it's just a general rule. EAX is almost always the return value. ECX is the counter in various rep operations. So the rep move that we're going to go back to in a second, ECX is going to be how many times that happens. You're not going to see that. It's just there. It's part of how, if you read the Intel docs, you can see that. I'm just trying to cover this stuff because it's going to be confusing if you don't know it. If you're reversing C++ code, you might see at the start of a function that they're using the ECX register for no reason. You can't figure out why. It wasn't referenced before. It didn't come from a stack variable. They're just using ECX, which violates some calling conventions or standard calling conventions. But in C++, you guys are familiar with the this object inheritance, right? If you have a function or a class that inherits from another class, that there's a this object, which is the parent, right? In C++, well, in assembly, the ECX register on the start of a function is going to be a pointer to the this object, which is extremely useful. In any of those rep operations, ESI and EDI are going to be pointing to the source and destination, right? Make sense? I'll show you that in a second. And then EBP, as Alec mentioned, is usually the frame pointer. However, it can be used as a general purpose register. That's up to the compiler. And real quick, a few of these registers can be split. EAX, EBX, ECX, and EDX can all be split into different bit widths of themselves. In other words, EAX you'll see in assembly. Sometimes you might see AX, AL, or AH. These are just different. They're all using EAX. They're just referencing different parts of it. AX is referring to 16 bits of it. AL is referring to the low 8 bits, and AH is referring to the high 8 bits, right? EAX is always 32 bits. But if you ever see references like this, it means that they're chopping it up into different parts. So you might see that in assembly. Just know that that's EAX. EDX is the same, except DX, DL, DH. All right, so back to these implicit operations. If you see a rep move like this, all that means is it's going to, rep is a prefix. It's opcode 66, I think. So the instruction is actually move SD. Rep is just meaning repeat it ECX times. Repeat it, whatever ECX is, that many times. And what it really means is rep move ESI into EDI. And now if you break it down even further, what it really means is EAX equals memcopy from source into destination ECX times. Does that make sense? So if a developer called memcopy on their buffers or whatever, it can get translated into a rep move SD. If you're looking in IDA, you're only going to see this right here, which is doesn't make any sense if you don't know what it's really doing, if you don't have an Intel doc handy. But what it's really doing is the following. And then you've got rep store, which does basically a mem set. Then you have rep scan, which basically does like a stircher where it's like looking for a value inside of a register, or inside of a buffer rather. So you can break one on any of these as well. You don't have to break one on functions. You can break one on a rep move and say, you know, or a rep scan in this case. So this will tell you something like the code is searching this pointer for this value foo. Stuff like that's useful. If you're, in other words, it's like if you're reversing a network protocol and you throw a bunch of A's at it, it would be nice to crawl the entire IDB for every rep scan that happens and set all those breakpoints in your debugger and have it tell you anytime any of them are hit and what is it searching for. Any questions on any of that? Now that we're done with the boring stuff? No? Good. Memory access breakpoints. So we showed those earlier. That's the BA command, right? Those are really useful because they allow you to, they tell you when an address is touched in any way. So think about it like this. In Alex's case, right? He had a call to receive. You know at receive that the receive gets pushed to buffer. That's the destination buffer of receive. Reads it off the network, puts it into a buffer. As soon as that happens, you can set a memory access breakpoint on the first byte of that buffer and then just let the process go. And the first time that code decides to read the data that came off the network, it will stop the debugger. You don't have to reverse all the crazy stuff that may happen in between. It'll just immediately go, here's where it's using your value, which is exceptionally useful. And then you can actually apply all that information, reverse stuff statically. Memory access breakpoints are really useful when dealing with dynamic memory. How many of you guys know what a memory manager is? How many of you guys have written a memory manager? You guys know what heap is? You've written a memory manager?
Okay.
I'm sorry.
That's
That's painful. Yeah, okay, so memory managers are basically, it's a way to allocate memory or get memory back of specific sizes that you request. Now, the manager part of memory management is all the algorithms that determine how to store that in memory. You know, we're doing doubly linked lists, are we doing trees, are we doing B trees, are we doing red-black trees? How is it all being stored in memory? So I have an analogy for that. You guys remember this game? Battleship? Yeah? Okay. So memory management is kind of like Battleship in that you call malloc, and it goes, all right, the most efficient place in my mind to put that allocation you requested. So this is memory space, first of all, clarify. I request with C code, malloc 10 bytes. It goes, all right, we're going to put you right there. Cool. Very simple. Then if I ask to malloc, 20 more bytes, it might choose to put me somewhere else. Generally, they try to be smarter than what I'm going to show you here. But basically, in Windows, the way it does it is it'll put it over here. It'll do like, this is simplistic again, but it'll do a doubly linked list. In other words, a forward and a back link. So each chunk points to each other, forward and back. Then you do stuff like malloc another one, and malloc another one, and malloc another one, right? So then you've got stuff like this. And the reason that dynamic memory sucks to analyze and why you cannot do it statically is at any point in any of those allocations, the memory manager can go, you know what, this isn't really efficient. I'm going to relocate this here, put that there, put them all in a, put the ducks in a line, in other words, right? And completely change what the memory layout looks like. And to the programmer, he has no idea. You never see that. You're agnostic to how that works. You just know I have a pointer to a buffer. I don't care where it is. The memory manager handles all that, which changes every single execution. And of course, if you freeze something, it updates it like that. So every time you run an application, it's going to, the back end of how all those structures are related to each other and the back end of the memory manager, completely different, which is why, it's all algorithm based. It's like, what is the most efficient way? If I run Internet Explorer and I open 100 tabs, back when Internet Explorer was one process, you open up 100 tabs and then you close 30 of them. The way the memory looks is going to be completely different compared to if you did the exact same process a second time, for many, many different reasons. So that's something that you'll have absolutely no idea about when you're reversing statically. But memory breakpoints can help you with this kind of stuff. WinDbg helps you inspect the heap with the bang heap extension. If you go to the help file, this is the kind of stuff you see. And bang heap basically lets you walk the entire heap. So remember that PEB thing I mentioned earlier, the process environmental block? That actually contains pointers to the start of the heap. And then if you invoke the bang heap command, it will actually traverse from the start of the heap through every single pointer to every structure that thing contains. And trust me, it is a hell of a lot more complex than just a doubly linked list. I mean, there's structures, inside of graphs, inside of all sorts of stuff. There's, if anyone's heard of look-aside lists and free lists and all that kind of stuff, it's all in the heap. And bang heap, written by Microsoft, allows you to traverse all that, which is exceptionally useful. Here are the two commands that I use the most for it. Remember, you need proper symbols for this. If you don't have symbols for the heap, then it's going to have absolutely no idea how to walk it. If you do bang heap 0-v, it's saying, give me a verbose output on heap number 0, which is the main heap, and it walks everything, verifying the entire structure, which is awesome when you revert. Like from the ZDI perspective, it's really useful for us because if I run a file someone gave us to the ZDI through whatever the target was, and it didn't crash, it might have crashed on their computer because their memory management was different than mine. Doesn't mean the bug's not legit. So what I'll do is I'll go ahead and break into the process and run bang heap 0-v, and it'll try to crawl the entire heap. And if any pointer is messed up, it'll tell you, like corruption found. Like, okay, cool. There was corruption. Let me investigate that. The heap is really, really finicky. There's trying to figure out why heap corruption occurs from the point of a crash is pretty difficult. You've got some other tools here to help you out. You've got bang heap p-a, and then you give it an address. This will actually give you, if you set up your process properly, it'll give you the call stack of who allocated that heap block, how big it is, and where it is located in memory, and where its metadata is located in memory, which is really useful. So just to clarify, bang heap, this right here is called a user mode stack trace database. And that makes sense, right? User mode, we're dealing with the user mode, we're not in the kernel. User mode stack trace database, meaning every time an allocation occurs, the process is actually saving the call stack as to who allocated that into a database, so that when you query it from your debugger, it can fetch it for you. And in order to get that to work, you have to use global flags. Global flags is an application that comes with WinDbg, or it comes with debugging tools for Windows. It's called gflags.exe. So if you go in gflags and you click on the image file tab and you type in the name of the process you care about, and you got all these crazy things you can enable to help you debug stuff. I'm not going to go into what they all are, but the ones you care about are create user mode stack trace database, and there's page heap. And page heap. Page heap is really useful. What page heap does is every time an allocation occurs, not only does it give you the allocation back, but it gives you a full guard page or a read-only page, a no-access page after the allocation occurred. Which means if you have any kind of heap overflow, as soon as the heap the buffer is being overflowed and it tries to write 1 byte beyond the end of that buffer, the debugger will stop and say, hey, we have a problem. You can imagine why that's useful, right? Like, stack buffer overflows, overwrite return addresses and all that. If you're dealing with the heap, you're overwriting the next heap chunk after you. Like, think of that battleship thing. If I'm copying into one of those buffers, I can just keep copying all over into other buffers, into metadata, into the pointers. Some of the first attacks on heap overflows were those pointers that I was showing in the battleship diagram there. The first attacks on that were overwriting those pointer values. So you'd overflow a buffer, and then you'd overwrite the pointers from the subsequent buffer. So page heap allows you to catch any of that happening. As soon as 1 byte is copied beyond the end of an allocation, there's a whole what's called a guard page behind it, which is basically anytime it's touched, the debugger stops. Super useful. Any questions on that stuff? Yep.
Is page heap implemented as like an operating system protection mechanism, or is that just a feature of WinDbg?
Depends how you use it. It's supposed to be a feature of WinDbg. When I'm doing stuff that I'm concerned about, I'll put page heap on. Sometimes I just attach a debugger to a process, just out of paranoia. But yeah, it's definitely not supposed to be a mitigation of any kind. It's got a crazy amount of overhead. I accidentally left it on Outlook.exe once for like a week, and I was wondering Outlook would take like 30 minutes to load. I had no idea why. It's because if I allocate 10 bytes it allocates a page. You know how big a page is on Windows? 4K, 4,096 bytes. If you allocate 1 byte, it allocates, 4,000 bytes behind that. So for every allocation, and there are a lot of allocations that occur in a process. All right, real quick, I'm going to go into some theory stuff real quick. Graphs and paths, right? This is a graph, right? Everyone understands that? This is exactly what you're looking at in IDA. If you hit the spacebar in IDA when you're looking at the dead listing, it'll go into a graph mode. If you zoom out from the graph mode, you'll see this. Red is a negative branch, green is a positive branch, and a blue is a, there's no condition. It's just a jump. So what's useful about this is if you're looking at any function, this is a very, very simplistic function, but if you're looking at a really complex one statically or even dynamically, you want to know, like, how much of this can I get to? When I'm reversing, the way that I do it is I actually color my nodes like this. So when I'm sitting there reversing, you can color every individual node in IDA however you want to. I have let me just show you guys what my IDA looks like. You can customize the shit out of IDA with,
Excuse me, are you talking about the IDA we have or the expensive version?
this is the expensive version, but I think you can do it with yours as well. Yeah, so, right, see this little icon right here? I think you've got it. And then if you zoom out, right? So you can do that with any function. And get out of the way. Hold on. Right, so before we were talking about how this is a graph. When you color stuff, I refer to it as a path, right? Oh, please. Okay. Right, so here's the function level. You've got a path through it. That's useful. That's the kind of data you can get from a debugger. If you're sitting in a debugger, you can set a breakpoint. Like, say you didn't have any of that. You can actually, in your debugger, set a breakpoint on every single head of every basic block. These are called basic blocks, by the way. Basic block is delineated by jumps, conditional jumps, usually. So in a debugger, you can set a breakpoint on all of these different things and figure out which ones were hit, and then take your information from your debugger, put it back in IDA, and then you know, okay, I hit those different basic blocks. Good to know. Same thing applies for function graphs, right? Setting a breakpoint on every basic block and every function in an entire binary is going to, it'll be unusably slow. But if you do it on function levels, you only have one per function. And I've done quite a lot of large reversing projects where this was immeasurably valuable. So here we can see, we start at this function IML321135, and you can see every function I got to is marked green. In fact, if you mark a function green, if you mark the starting basic block of a function green in IDA, and then you use that graphing, the right-click the function name and you do graphing, like I mentioned earlier, any function that you've colored the first node of will appear colored in this graph, which is pretty useful. So that's essentially what's referred to as hit tracing. You generally don't want to do hit tracing with breakpoints, just because a breakpoint is actually a breakpoint has some overhead associated with it because it does a context switch in the kernel. Don't worry about that. Most people do it with instrumentation, but I don't want to go into that because it's a little more complex. But basically, this process is called hit tracing. You can hit trace inside a function. You can hit trace on functions, wherever you want. So imagine having your entire IDAPRO database marked up with every single location that was hit with a debugger. So say you're looking at Windows Media Player, you have the executable in IDA, you don't know anything about it, and then you say, all right, let me run an ABI file in Windows Media Player live. Gather all the different functions that were hit, and put it all back into IDA. Now you know, okay, here's all the stuff I want to look at. Looking for vulns, here's how it parses all the different parts. Like, you give it, then you can diff the two, right? So I can give it, let's say a ABI encoded with whatever xvid versus divx, right? So you can get all the hit traces from a run of an ABI encoded with divx, and then do the same thing with xvid, diff the two, and go, that is the point at which it decided that this was a different codec, right? And then you can enumerate all the other codecs it might reverse or it might